We're going to go ahead and look at some problems in Chapter 7. This is problem number 34. So you can see the description here. And the first thing I do, of course, in these problems is try to draw what I know about the problem and sort of set things up and then decide how I'm going to work on the problem. So we have a sled plus a passenger. Okay, so we have a person on the sled. With a total mass of 50 kilograms. All right, so we've got an mg that's down, pulled across the snow at constant velocity by force directed 25 above the horizontal. Okay, so there's the force pull. This is 25. Let's see, here's my surface. It's supposed to be flat. And we've got friction. We're also going to have a normal force. It's not going to quite be equal to mg because we've got a component of this pull force right here, F pull, this F pull Y is this arrow and this arrow, the purple and the green are going to equal the mg down. And then we've got this force pull in the x direction. Okay, maybe we need all this stuff, maybe we don't. I'm just outlining what we have. Okay, so let's go ahead and write down information so we know the distance this goes is 20 meters and the mass is 50 kilograms. Okay, so we're supposed to find the work of the applied force. So for part A, we need the work of the pull, which would be just F pull X times this distance, the 20 meters. The work of friction, so B is going to be the work of friction. So that would be the force of friction times the 20 meters, but that would be in the negative direction because friction is opposing this. The angle, if you like, it's friction times the displacement times the cosine of the angle between friction and the displacement, which would be 180 degrees, which is equal to -1. Okay, and part C is the total work. So work total is equal to the change in kinetic energy. I mean, I can add up all the work from all the forces, the normal, the weight. The normal's not going to do any work because it's perpendicular, as is the weight. If you want to calculate, for example, the work due to the weight, that would be mg times the displacement times cosine of 90 degrees, and cosine of 90 degrees is 0. So that's how you get at the work due to the weight is 0, and in this case the normal force is 0. But we can also just say the total work is the change in kinetic energy, and if it's at a constant velocity, then that means kinetic energy final minus kinetic energy initial, since kinetic energy is 1/2 mv squared, 1/2 mv final squared minus 1/2 mv initial squared. Well, these don't change, so these are equal to each other, so it's 0. So actually part C of this question is the easiest one to answer. So sometimes you can skip down to the different parts and get that answer right away. What it also means is that these two should be equal to each other. So we'll see if we get that when we get going. All right, so now to find the work of the applied force of the friction, we actually need these force values. So we actually need to do some force F equals ma type stuff, okay? So what we're looking for really to get this problem done is these force values, both of which are unknown. It's just a pulling force. But we know that in order to have constant velocity, that this force in the x direction must be equal to this force, the kinetic friction, which of course is what we would get from this. So we know those forces must be equal. So I'm going to do my SOHCAHTOA and recognize that the force pulling in the x, that's the cosine, that's the adjacent one, so that would be force pull times cosine of 25 degrees. And force pull in the y would be force pull that's this one over here, sine of 25 degrees. Okay, I'm going to redraw my force diagram just so that I have it conveniently nearby. Here's our force diagram. I have mg down, I have force normal up, I have the pull, which I've broken into two, force pull y, and I have force pull x, and then I have the frictional force. Okay, and I have my equations for the force pull in the y direction. Just rewriting these is force pull times sine of 25 degrees. Force pull x is equal to Fp cosine of 25 degrees. Okay, so we'll just start down here, and we know we're looking for the forces, so we can find the work. So to do this, I just need to do sum of the forces in the x direction equals mass times acceleration in the x direction, but I know because I have a constant velocity that acceleration is 0. Similarly, sum of the forces in the y direction equals mass times acceleration in the y direction. That's also 0, so I'm just going to write down my equations. So from this Fx, I've got k, my friction, kinetic friction in the negative direction, plus force pull in the x, which is force pull cosine 25 degrees, is equal to 0. Similarly, in the y direction, I've got three things. I've got the normal, the force pull in the y, which are both up, so force normal, plus force pull in the y, and then I've got mg minus mg is equal to 0. And so force normal plus force pull sine of 25 degrees minus mg is equal to 0. Okay, let's look at the number of knowns and unknowns we have. We know m times g. M was, at least I think we do, yes, m was 50. So m is 50 kilograms. So m times g is 490 newtons. I don't know this. I also don't know the normal force. It has to adjust, and it's going to depend on this pulling force, so that's unfortunate. I also don't know this, and I don't know that. So it looks like I've got 3 unknowns and only 2 equations, so that's sort of a problem. But we can recognize that this is equal to mu times force normal. And I think we were given mu. Yeah, here's mu of 0.2. Okay, so we have a mu of 0.2. Then we can plug that in, and we can solve one for the other, basically. In other words, I'm going to put this expression, I'm not going to put the numbers in yet, just so I can do the algebra. I'm going to put this expression in here. And then I'm going to, so I'll have minus mu sub k force normal plus Fp cosine 25 degrees equals 0. I'm going to take this and solve for the normal force. So I've got Fp cosine 25 degrees is equal to, bringing this to the other side, mu sub k force normal, dividing both sides by this, gives me then that my force normal is equal to the pull force times cosine of 25 degrees over mu sub k. Now, I just need to substitute that into my y equation. So I need to take this equation that I have right here and plug it in right there. So that, substituting that in, I get Fp cosine 25 degrees over mu sub k plus Fp sine of 25 degrees. I'm going to add mg to both sides, so I get a plus mg. Now I can actually solve for my force, and then I'm almost done, finally. Again, this is just some algebra, right? So I've got FP, and I've got cosine of 25 degrees over mu sub k, plus I factored out the FP, sine of 25 degrees equals 490 newtons. At this point, it's probably useful for me to just find out what these numbers are, so I need to plug this into my calculator. So these are the numbers that I got when I plugged this into my calculator. So this is 4.95 when I add these together, and then I'm going to divide both sides by that, and I will get the force push is 490 newtons divided by 4.95, which is about 100, right? Very close to that. So 98.9 newtons if we want, 99 newtons. And then from that, I can just use any of these equations to then calculate the friction force, but I don't actually need to do that at this point, because to find the work done, I just need to find the work is the x component of the force. So my force from down below was about 99, so I have this is 99 times cosine of 25 degrees, and that is right at 90 newtons. Okay, so I have 90 newtons times 20 meters, and so that's going to give me 1800 joules, and then I know immediately this is minus 1800 joules, because these forces have to be equal and opposite. These forces are equal to each other, it's just this one points in the other direction.